Hi, I'm Peter, and today I'm going to talk about our paper, A Stress-Free Sum of Squares Lower Bound for Coloring, which is joint work with Pravesh K. Kothari, and we're both at Carnegie Mellon University. So let's get to it. Here's a graph. The vertices are the blue dots on this blue ring on the outside, and the edges are the lines connecting them. There's a lot of blue vertices. And I promise that I sampled this graph from GN half, which is a random graph distribution on graphs with n vertices, where every edge between any pair of vertices is present with probability half, and they're all sampled independently. And it is known that the chromatic number of such graphs is about n over 2 log n with high probability. And this chromatic number chi g is simply just the minimum number of colors needed to color the graph G. And the question I want to ask is, can I efficiently verify that the graph G is not k colorable, say for k equals 3? And this is actually pretty easy to do because a random such graph will have a four-clique with high probability, and you can efficiently find such a subgraph, and that will certify that the graph is not 3 colorable. But what about, say, k equals 10, k equals log n, or even k equals n to the 0.3, k equals square root n, or k equals n to the 0.99. Like, for what k can I efficiently verify that the graph G is not k colorable? So this is the task of refuting the statement that chi of G is strictly less than k. In other words, we are trying to certify that the graph G has no k minus 1 coloring. And we can formalize this by defining a refutation algorithm. And it's simply an algorithm A that outputs a value AG, such that A of G is always less than or equal to the chromatic number of G. And this means that whatever value A outputs certifies a lower bound on chi of G. Namely, if A of G outputs, say, 5, then we know that chi of G is at least 5, and therefore G is not 4 colorable. On the other hand, we could, as the definition has stated, the algorithm A could simply always output, say, 1, and wouldn't say anything interesting. So we wanted to also have the second property that is useful, namely that with high probability, it is at least, A of G is at least some k for when G is sampled from GN half. And when this happens, we'll say that A refutes the existence of a k minus 1 coloring in G with high probability. So what refutation algorithms are known? Well, the Lovash theta function, or more or less equivalently the degree 2 sum of squares SDP, gives a refutation algorithm when k is about square root n. But recall that the chromatic number is about n over 2 log n, so this is actually far from the true value of chi of G. And the fundamental question we can ask is, can we do better than k about root n? And given that the title of the paper has the words lower bounds in it, you should expect the answer here to be no, and indeed that is what we prove. Our main result shows that with high probability over G, degree little of log n sum of squares cannot refute the existence of an n to the 1/2 plus little of 1 coloring in G. So let's break this down a little bit. So first off, the negative answer is actually not surprising, especially given prior work on related questions like independent set. Second, this is tight in the degree d, which is this little o of log n in the theorem, in that degree O of log n SOS can refute all the way up to n over log n, so basically at the chromatic number. So it can basically get the truth. And it's also tight in k in the sense that degree 2 SOS can refute when k is about root n, so up to this n to the little o of 1 factor, it is more or less tight also. And this is the first lower bound for coloring that extends beyond the degree 2 sum of squares SDP for any SDP hierarchy. And it rules out even n to the little o log n time SDP algorithms. I should mention here that I say cannot, but there's an asterisk there, so there are some caveats that I will explain in a bit. But for now, I'm going to ignore the caveats. And finally, our proof is stress-free in the sense that it's actually very simple. Like most sum of squares, lower bounds require some very complicated analyses of the spectral norms of random matrices with intricate dependencies between the entries, and we don't need to do this. On the other hand, we do rely on prior work, which does have to do such analyses. So in some sense, if we wanted to prove a result from basic principles, it wouldn't be stress-free, but we're assuming prior work here. So to see why the actually negative answer is not surprising, I'm going to first explain some known results about independent set, which is a very related problem. So we're going to take just a small detour before returning to color. So let's talk about refuting independent set. So like the case of coloring, we can just try to refute the existence of an independent set of size, say, omega in a random graph from G n half. And this is a well-studied problem. Typically, it's a study of the name-planted clique, and the connection is simply that a clique in G is an independent set in the complement of G. So these problems are basically the same. And what is known? Well, the truth is that G only has independent sets of size up to, say, like 2 log n with high probability. But degree 2 sum of squares can only refute for omega about square root n. And there is a nice lower bound showing that degree little o of log n SOS cannot refute for omega smaller than square root n. So basically this root n is the limit of sum of squares. And kind of intuitively, if sum of squares is failing to refute that there is no independent set of size smaller than like square root n, we should also kind of intuitively expect it to fail to refute that there is no root n color. And why is this? Well, a K coloring is simply a partition of vertices into K independent sets. So if G has no independent set of size omega, then we know the chromatic number has to be at least n over omega. Unfortunately, the statement we are looking for is the converse of this, which is that if we cannot certify that G has no independent size omega, then we want to say we cannot certify that chi of G is at most n over omega. So that doesn't follow from this. But nonetheless, the intuition as to why one might expect this to hold should perhaps be clear. So we will, in fact, prove a result via reduction within SOS to the independent set lower bound on the previous slide. But because this implication is not just like a generic one, our reduction will actually be fairly non-trivial. And this is unlike, our reduction is unlike prior reductions within SOS, primarily those based on the work of Tulsiani, because our reduction doesn't satisfy a particular property called pointwise completeness. So what is a pointwise complete reduction? Well, like a normal reduction, it is a map from instances of problem A to problem B. The direction of the map is actually reversed from maybe your typical algorithm's definition, because we're thinking in terms of lower bounds here, but that's fine. But the pointwise completeness is property 2 here, which is that it also comes with a map that basically will take any solution x of the instance IA to a solution y of IB. So what does that mean for coloring an independent set? Well, for our case, problem A is independent set, problem B is coloring. And so to apply this Tulsiani type framework, we need to have a map that takes an independent set of size omega in G and constructs an n over omega coloring from it. But this is just clearly doesn't make any sense, because just because G has some independent set of size omega doesn't mean it has an n over omega coloring. To have an n over omega coloring, it needs to have a lot of such independent sets. So such a map just can't possibly exist. So this kind of pointwise complete style reductions fail completely here. And our reduction is in some sense completely new because it circumvents this problem. Okay, so that was just a small detour independent set. But before I can give you the proof overview, I have to actually take a larger detour just to explain sum of squares. So my apologies that the slide is going to be very, very dense, but too bad. I don't know. There's no way to get around it at this point. So let me just explain what the sum of squares algorithm does. And for simplicity here, I'm going to explain the sum of squares algorithm over the hypercube, which is all we need for the purposes of this paper. So the input is a degree parameter d and a system of polynomial constraints over n variables. And the output is an n to the O of d time. The algorithm outputs a fake distribution over solutions over the hypercube to these constraints, or else outputs no solution. So the algorithm can't actually output a distribution because that would imply p equals np essentially. So instead it outputs something that's called a degree D pseudo distribution, which is an object that pretends to be a distribution to low degree polynomials intuitively. And this is just simply a linear operator on degree D polynomials satisfying the following properties. So first off is this pseudo expectation of 1. So this e tilde is sometimes called a pseudo expectation. Pseudo expectation of 1 should be 1. Pseudo expectation of f squared should be greater or equal to 0 for every polynomial of degree at most d over 2. And these properties I'm going to list off should all be ones that feel very natural if you thought of this e tilde as an actual expectation over distributions over solutions to these constraints. So property 2 says that pseudo expectation of like xi squared minus xi times f is equal to 0, which should intuitively, again, be a constraint you think to hold, because like if you want xi to be either 0 or 1, then xi squared is equal to xi, so this should hold. For constraint 3, it's a similar thing, just for the constraint pj equals 0. And constraint 4, there's a slight difference for inequality constraints where I have a constraint of the form pj greater or equal to 0. But here I just want this expectation of f squared times pj to be greater or equal to 0. And here there's always a constraint on the degree of f, but the limitation on the degree of f is simply so that the polynomial inside the square brackets always has degree of most d. And if you want, you can pause the video and just verify to yourself that if e tilde is in fact the expectation of operator for distribution mu supported on solutions to the constraints, then these properties 1 to 4 should trivially hold. So this pseudo expectation in some sense is like a generalization for low degree polynomials. So that might be a lot to digest, but let's just explain briefly what this means in terms of coloring. So coloring, the input are variables xi, c, which you should think of as the indicator of the event that like, vertex I receives color c. And the constraints, well, we need to capture what it means to be a coloring in terms of these polynomial constraints. So we can first add the constraint that xic times xjc should be 0 if I is connected to j. And this just means that like xi cannot be, or I cannot be assigned color c, while j is assigned color c if they're connected, which is, you know, a normal constraint to have for coloring. Then we also want to say that I cannot receive both colors c and c prime at the same time. And finally, we want to say that vertex I receives exactly one color, which means that the sum over all colors of xic should be exactly 1. And the output is either not satisfiable or else a linear, the pseudo expectation on degree d polynomials satisfying following constraints. The first two are the ones from the previous slide, and then I'm just going to interpret the more generic definition of the previous slide in terms of the actual constraints we're given here. So that means like the edge constraints correspond to bullet 3 here, the color constraints are bullet 4, and the sum constraint is bullet 5. And I've omitted the bounds on the degree of f, but it's always such that the polynomial within the square brackets has degree of most d. And the SumofSquares algorithm will output not satisfiable if no such pseudo expectation exists, and otherwise it will find one. And how do we turn this into a refutation? Well, you first pick a parameter d, and then a of d can efficiently compute, n to the o of d time, the smallest k such that such a pseudo expectation exists. And notice that this pseudo expectation existing depends on k because the number of variables we have is a function of k. And furthermore, we should notice that this k will always be at most the chromatic number of g. And this is because if we set k to be the chromatic number of g, then indeed such an e tilde exists simply by taking e tilde to be a distribution over k colorings in g, where k is the chromatic number, so therefore, in particular, a coloring exists. Therefore, we can see that in order to prove our main theorem, we just need to show that such an e tilde exists for k about root n with high probability over g. So now I'm just going to take a brief moment to mention the caveat. There was that asterisk on when I stated our result. So let me just explain now what that is. So we only prove that e tilde exists that's satisfying some weaker system of constraints. So on the right here, I have put the older constraints and what it means in terms of the pseudo expectation. And on the left, I'm going to put the system of constraints that we actually satisfy. So the edge constraints are still there, but we replace the color in some constraints by the inequality constraint here. And in terms of the pseudo expectation, the first three things are the same, and the four bullet points 4 and 5 on the right are replaced by this constraint on the left. And intuitively, really, the only difference here is the constraints on the right are asserting that vertex I gets exactly one color, whereas the constraints on the left are asserting the vertex I gets at least one color. And in terms of what this corresponds to coloring, well, they're actually the same. Both our systems are satisfiable if and only if the graph is k-colorable. But formally, the constraint system on the right is a formally stronger constraint system in terms of the refutation algorithm. Okay, so now on to the proof, which I've promised is not going to be too complicated. So we're going to prove our theorem via reduction to the independent set lower bound that we know exists. So by that paper, we know that there is a degree little of log n pseudo expectation for independent set, which means it satisfies the following properties. So property 1 and property 2 are the same as always. I've replaced the variables xic with yi just to avoid confusion between the independent set variables and the coloring variables. But you should think of yi here as just the indicator that vertex I is in the independent set. We have the same, more or less the same type of constraint for the edges. And constraint 4 says that the probability that vertex I is in the independent set is at least 1 over root n, which means that the independent set and expectation will have size like root n. And property 5 is an eigenvalue lower bound on the pseudo expectation, essentially. And it's saying that the pseudo expectation of f squared is at least n to the minus O of d times the L2 norm of f squared, where we think of the L2 norm of f as think of f as a polynomial, but we think of it as a vector where it's just the coefficient vector. So this is the sum of the squares of the coefficient vectors. And there's this other small technical detail that we need to have this projector pi g to project out the polynomials that we have hard-coded to have pseudo expectation 0 by constraint 3. And we want to show that this implies that there's a degree little o log n pseudo expectation satisfying the following properties, which are the ones from the previous slide. And we're going to add this extra detail, extra property e, which is that we want the number of colors k to not be too large, and we want it to be about root n. And here I'm just going to suppress polylog factors. They're not too important. And you should think of this intuitively as the thing on the left says that SOS thinks that there is a distribution mu over independent sets where each vertex is in the independent set with some reasonable probability. And we want to show that this implies that SOS thinks there is a distribution mu prime over root n colorings. So let me now explain the key idea of our proof. So instead of these statements about what SOS thinks, let's think of an ideal case where we suppose that there actually is a mu over independent sets where this holds. And we want to now construct a mu prime over root n log n colorings. And here I've put the log just to be more precise. So how do we prove this? Well, namely, we just draw k independent samples from mu. So if we think of the set of vertices v of the graph, let's say this is S1, S2, S3, S4, and we'll just sample independent sets, k of them, for k root n log n. And we should notice here that if these independent sets we sample cover all the vertices in V, then G is in fact k colorable. And this is because these independent sets are namely the k color classes we use in the coloring. There is the slight detail that a vertex could appear in more than one independent set, but this is actually not this is not a big deal at all, because you can simply just remove it from all the other independent sets but one, and then this doesn't change anything. So this still holds. And what's the probability that this good event happens? Well, the probability that some vertex is not covered is at most 1 minus 1 over root n to the k, because there are k samples, and it's not in 1 with probability at most 1 minus 1 over root n by the hypothesis. And we can upper bound this by e to the minus k over root n, which is then 1 over poly n, because k is root n log n. And so we just union bound, and we then get that the independent samples we drew gives a k coloring with high probability. And moreover, we actually get a distribution mu prime on such k colorings just by conditioning the distribution where we drew independent samples on this event. So now let's apply the key idea to more or less give our lower bound. So on the previous slide, we discussed what happens in distribution land, where we assume we have a distribution. And this is like the ideal case. So we start off with an expectation operator of a distribution on independent sets. And our first step is to draw k samples, which means the expectation of the k sample distribution is just the tensor of the k tensor of the original expectation. And then we condition on this event. And this gives us our distribution over colorings. Unfortunately, SOS land, we have to deal with pseudo expectations, and this is a lot more annoying. So we start off instead with an e tilde over independent sets. Step one is fine. We can tensor this operator, and that still works. There's no issues here. And this more or less simulates drawing k independent samples from the pseudo distribution. But the issue comes in the conditioning step. So this breaks. And the reason it breaks is because conditioning in SumofSquares for pseudo expectations requires like conditioning on the indicator polynomial of this event. And unfortunately, the indicator is this nasty expression. And this is, if you stare at this for long enough, you'll see this is like a degree nk polynomial. It's like a very, very high degree polynomial. So this just doesn't work. So here I put at the bottom like the thing we're trying to prove just for reference. So we're going to instead just set e tilde prime to be this tensor thing. And let's see what happens. So first is we should observe that, in fact, properties A, B, and C all hold for free. And it's just inherited by the tensor structure. So this checks the first three properties that we want. But we now need to show how to satisfy properties D. And this is, the surface maybe looks more tricky. Like, how are we going to modify this e tilde prime so it satisfies this? And kind of the funny trick is that we just don't. We'll show that D holds without modification. And this might seem a little weird because, this kind of doesn't really hold for distributions because there is some small probability that a vertex will not appear in any of the samples of the independent sets that we draw. But the intuition is that, well, the pseudo expectation of the sum of this thing is about like k over root n, and k is like root n log n. So this is like log n or something, maybe like log to the 10 n. And you could hope that low degree polynomials somehow can't see this small probability event that like sum of xic is 0. And if it can't see this event, then it should probably satisfy the constraint. So you could hope that this holds. Okay, so let's finish the proof. We know A, B, C hold. Remains to argue D. And we do this by showing this eigenvalue lower bound, this property, mysterious property 5, implies a 2 to 4 hypercontractivity for E tilde prime. And then this gives us this following equation, which essentially is saying that, if we look at this thing we're trying to show is greater or equal to 0, it's at least 2 minus 1, or the minus 1 is exactly this thing that we're subtracting off, minus this e to the minus k over root n that we kind of saw earlier, times n to the d squared, and the n to the d squared comes from taking this n to the minus od, and raising it to the dth power. Okay, and that's times a pseudo expectation f squared. And now just by taking k to be like root n d squared log n, which is at most root n log cubed n because of what d is, we get that the right hand side is at least 0. So then that finishes the proof. Okay, so that means property D holds, and we see that we take k to be about root n, so property E also holds. Okay, so just to summarize, our result says that with high probability over a graph drawn from G 1/2, degree little o of log n SOS cannot refute the existence of an n to the 1/2 plus little o of 1 coloring in G. And the only caveat here is that we're using this weaker constraint system. And we already explained that it was tight in D, and it was tight in K. And our proof is simple because it's using this idea of repeated samplings of independent sets to reduce to the independent set lower bound. And our reduction is non-pointwise complete because it's abusing the fact that like the independent set lower bound is not just giving like a pseudo distribution over independent sets, but rather a pseudo distribution over independent sets where like that's like roughly like uniform-ish, because like every vertex appears in the independent set with like some reasonable probability. And yeah, this is the first lower bound for coloring beyond degree 2 sum of squares. So finally, I just want to end by discussing the weak versus strong formulation. So the weak formulation is given by the name, it's formally weaker. But like morally, it's not like doesn't feel that much weaker, because the difference is like you're merely allowing a vertex to get multiple colors, and somehow how can this really like change things? And an important point to notice is that the degree D lower bound for k colors for either formulation gives a lower bound for independent set. So really like the weak formulation itself can't be that weak, because at the very least it's implying independent set lower bounds for sum of squares, which themselves are like very non-trivial. But the technical issue as to why we can't get the strong constraints to be satisfied is that these equality constraints are exact, meaning they need to be like exactly 0, and this becomes just harder to handle technically than inequality constraints. And this is an issue even observed in the independent set lower bound, where the independent set lower bound did not satisfy, of this BHK plus, did not satisfy a very natural set size constraint of like saying the sum of all the yi's should be equal to omega, meaning that the independent set you sample should always have size exactly omega, but it only satisfied this in like pseudo expectation. And in fact, in this case, it didn't affect anything. And this is actually a paper in this conference by Pang, which proves that there is an independent set lower bound that satisfies the set size constraint also at like roughly omega about root n. So morally, the fact that the BHK plus independent set lower bound didn't satisfy this constraint, was just like a technical issue and not like a like substantial like qualitative issue here. And therefore, it would also kind of be surprising if this weak versus strong thing matters. It seems to be more like a technical issue that we don't know how to overcome, rather than like something fundamentally different with the problem statement. And that's all I have. Thanks for watching. And you can find the full version of this paper on arXiv.